Welcome back, everybody. In this video, we will be covering the third part of Lecture 14. The topic is put option prices in the Black-Scholes option pricing model. Okay, let's get started. In the previous video, we used the Black-Scholes model to calculate the price of a European call option. We now want to use the Black-Scholes model to price European put options. To do this, we're going to have mostly the same assumptions as before. There is a non-dividend paying stock S. The price of that stock today is S0 and the future payoff ST is a random variable. The stock has an annualized return volatility of sigma, and the stock's returns are normally distributed under the risk neutral or Q measure. We consider a European put option on this stock with a strike of K and a maturity of capital T. And we want to price this European put option using the Black-Scholes model. It turns out that the Black-Scholes model price is given by the following equation. The put price is going to be equal to the present value of the strike times phi of negative D2 minus the current stock price today times phi of negative D1, where D1 and D2 are just constants that take in observable inputs and output constant values. And phi, again, is the standard normal cumulative distribution function, i.e. the z-table. Computing the Black-Scholes put price from this formula is just simple plug and chug, but it can get a little messy because of all these inner terms, such as the D1s and the phi's. Okay, and so the way I usually like to do it, just like the call, is to do a three-step process. In the first step, what I usually do is I go out and I calculate D1 and D2. The formula for D1 and D2 are the same exact as in the call option. They take in our 5 inputs to the model: the stock price, the strike, the risk-free rate, the volatility, and the maturity, and they output 2 constants, D1 and D2. It's just simple plug and chug. You then take the opposite of these D1s and D2s, and in step 2, you calculate the phi's. So in step 2, given D1 and D2, you take the norm as dist function of the opposite of them. So remember, this phi is the cumulative distribution function of the standard normal distribution. It's going to output a cumulative probability that falls between 0 and 1. And there's many ways to go about getting this probability. The easiest way is to just go into Excel, type in the norm.s.dist function, which takes in an argument x, which is the value of the standard normal random variable. And the second argument is true, which means use CDF instead of probability density function. Once you have the phi's in step 2, then every step 3 is just plug and chug. So in step 3, it's just the original put price formula. Okay, you plug in everything here as observable, plug in the present value of the strike, you've computed phi of negative D2, you plug in the current stock price, and you've computed phi of D1. So in summary, Black-Scholes put price formula is very simple once we see that it's just a bunch of observable inputs that we need to plug in. We start by working inside out, calculate D1 and D2, then calculate the phi's, throw everything together, and we're going to get the Black-Scholes put price formula. Okay. One thing to notice that's kind of interesting is that the formula for the Black-Scholes put option price is very, very similar to the Black-Scholes call option price formula. So if you recall the call option price formula in the Black-Scholes model, it says C0 is equal to S0 times phi of D1 minus K e to the negative R times T, phi of negative, D2. While put option formula was equal to K e to the negative R times T, phi of negative D2 minus S0 times phi of negative D1. So look at these two formulas, compare and contrast. You see that the put is really, really similar to the call price formula. You just reverse the two terms in the equation, okay? And then you use negative D1s and D2s instead of positive D1s and D2s. Okay? The similarity between these formulas is not a coincidence. Rather, it's actually a result of put-call parity, and it's forced to be this way. Now, what we're going to do on this slide, as a bit of high level right here, is we're going to derive the put option price formula from put-call parity and the call option price formula. I don't expect you to remember all the math on the slides. However, walking through it once is useful and instructive for the general idea of a derivatives pricing. It's a great way to test your knowledge of put-call parity heading into something like the final exam. So suppose we know what the Black-Scholes call option price formula is. What we're going to now show is that we don't need to go out do all the math to find the put option price formula. What we can just use instead is put call parity. So we start by writing down put call parity in this first line. Put call parity says that the price of a protective put is equal to a price of a fiduciary call, or equivalently that the price of a put is equal to the price of a fiduciary call minus the stock price of a put. What we do in the second line of this equation is we just assume we know the Black-Scholes call option price, and we plug in the formula for C0. So we take the Black-Scholes call option price formula, we plug it into C0 down here, and this is going to be the term in the brackets, and it's just going to be a simple substitution in the second line. In the third line then, we group like terms. There's two terms that have k e to the negative rt in front of them. One has a phi of d2, the other one has a plus 1. So we group these, k e to the negative rt, 1 minus phi of d2. Then we group the two terms that have s0 in front of them. It'll be 1 minus phi of negative d1. Okay? So this gives us the put option price in the Black-Scholes model. If you use this formula in the third line right here, you're going to get the exact same answer as if you were to use the formula in the first slide. But to get to the formula in the first slide, all you have to do is make a little simplification that applies some properties of the standard normal distribution. Okay? In particular, what we're going to apply is the property that the normal distribution is a symmetric distribution. And the symmetry property of the normal distribution says that the area in the left tail of a bell curve, okay, area in the left tail, is always equal to the area in the right tail of the bell curve, this bell curve split at 0, for a symmetric distance from the mean. Okay, so if you have x and minus x, then the area to the right and to the left of these two are going to be the exact same. Mathematically, what that means is the area to the left of negative x is just equal to phi of negative x. This is just a CDF formula. The area to the right of x is 1 minus phi of x, if you remember your stats 101. And so what we can do is we can take this and we can plug it in to these two over here. So 1 minus phi of d2 by the symmetry property of the normal distribution is just phi of negative d2. 1 minus d1 is just phi of negative d1. And so you take these, you plug them in, and out is going to pop the Black-Scholes put option price formula that we learned about in the first slide. P0 equals k e to the negative rt, phi of negative d2 minus s0, phi of negative d1. Okay, why did we do this? Why is this instructful and easy and useful to understand? One is just practice with put call parity. And two is to highlight a fact that goes on in real life option pricing. In real life, quant desks or pricing desks only price or develop models for calls or puts. They never develop a separate model for each of the call or the put. So when they do the higher end math, they have much more advanced models than Black-Scholes. When they do the math to calculate what the price should be, what they do is only form the model for either a call or a put, and then they always just use put call parity to derive the price of the put from the call. It's sufficient to price either the put or the call, in order to price the other on most quant desks. Okay, it reduces a lot of work and a lot of mathematical equations. Okay, so here's a practice problem for Black-Scholes put options. We'll work through it. I'll give you a second to read it, and then we'll solve. Okay, so let's work through it. So today's price, we have Boyd Gaming. Boyd Gaming is a stock, okay, non-dividend paying stock. Today's price of that stock is $15, and it is expected to have an annual volatility of 30% over the next year. Okay, we're interested in a European put option on Boyd Gaming with a strike of $20 and a maturity of 1 year. We assume there's no arbitrage and the Black-Scholes model assumption holds, and the continuously compounded risk-free rate is 5%. We want to do two things in this problem. First, get some practice with the Black-Scholes put option pricing formula by calculating the Black-Scholes price of this put option. And second, refresh our mind of put-call parity and price the otherwise identical European call, that means the same strike and the same maturity, on Boyd Gaming. So to solve this problem, we start by writing down our inputs. Part 1 is to just calculate the Black-Scholes put option price. Stock price today, Boyd Gaming, is $15. This stock has an annualized volatility of 30%. Risk-free rate is 5%. And we're interested in a European put option with a strike of 20 and a maturity of 1 year on Boyd Gaming. These are all the inputs we need to calculate a Black-Scholes put option price. Formula for this is P0 equal to present value of the strike times phi of negative D2 minus S0 times phi of negative D1, where D1 is equal to natural log, remember, S0 over K plus R plus 1/2 sigma squared times T, all over sigma root T, and D2 is equal to D1 minus sigma root T. Okay. Plug and chug, solve this problem, work inside out, start by calculating D1, D2, take the opposites, get the phi's, and plug everything in. D1 is given as follows: log stock price 15, strike 20, plus R 5%, plus 1/2 sigma squared, 30% squared, times T1 over sigma root T, 30% times root 1. Okay. This is equal to what? Check my math on this, plug it into your Excel or your calculator, negative 0.642. D2 then is you take D1, subtract sigma root T. D1 we just calculated, negative 6.642, minus sigma, 30%, root T, 1. Root 1 is 1, so this is negative 6.642 minus 0.30, negative 0.942. Okay. We have D1, D2. Our inputs, our formula is actually going to use the opposites of these, so let's just calculate them out. Negative D1 is just negative 1 times D1, 0.642. Similarly, negative D2 is equal to 0.942. Check on your Excel. Okay. We have the D1s and D2s. Next step is step 2 is to compute the phi's. Phi of negative D1, let's start with that one. Many ways to do this. You could numerically integrate it yourself. You could look at the Z table. My preferred way in this class, norm.s.dist. Okay, negative D1 is what? 0.642. What's the second argument? It's true. It says CDF, not PDF. Okay, what is this equal to? It's a number between 0 and 1. Okay, 0.7397. Similarly, 5 negative D2. use our favorite norm.s.dist function. Negative d2 is 0.942, true, equal to 0.8270. Let's plug everything in. We've got what we need now. P0 equal to K20 e to the negative r times t times phi of negative d2, 0.8270, minus the stock price today, 15, times phi of negative d1. Plug in all this. You're going to get, check on your Excel, 4.64. So the Black-Scholes put price is $4.64. Okay. Straightforward, just plug and chug. A lot of different, a lot of intermediate steps, but check your work along the way and you should be fine come test time. Second part, we want to use put call parity to derive the price of an otherwise identical call option. We could just use the Black-Scholes call option formula. We'd get the same exact answer, but put call parity is going to be a lot faster and simpler. Put call parity says that fiduciary call is equal to a protective put, or similarly, a call is equal to a protective put minus the present value of the strike. Plug in inputs. Put price, 464, we just found that out, plus 15 minus present value of the strike. What is this going to be? The call price, plug in all this on your calculator, you're going to come up with 61 cents. So the Black-Scholes call price is 61 cents. You'll get the same exact answer if you were to just use the Black-Scholes formula. This is just going to be a way quicker way to do it and go about it. Okay, a couple things to notice is one thing to notice is that the put price is much higher than the call price, despite the put suffering from deferred payment while the call benefits from it. Why is that the case? It's because the strike is way above the stock price today. This is an in the money put and out the money call. Put benefits from higher strikes, right, to sell at a higher value, so it's going to be higher in the price. Okay, so that's a practice problem. One final slide before we take a quick little break. So the Black-Scholes put price is very simple. The formula is, okay, it's elegant, it's mathematically beautiful. One line equation. Okay. However, it also has a very economic interpretation. Just like the call, it's the price of the replicating portfolio. Essentially, you can replicate the payoff of a put option by taking a portfolio of two different options. The first option is an option that pays 1 if the stock price falls below the strike. And the second option is an option that pays a gross rate of return if the stock price falls below the strike. Okay. What you do is you go long K units of the option that pays 1 if the stock falls below the strike, and you short S0 units of the option that pays a gross rate of return. Construct this portfolio and look at the payoff. I guarantee you that it exactly mirrors the payoff of the put option. Okay. Because these two payoffs are the same of these portfolios, the prices must be the same. So the price of the put option must be the price of the replicating portfolio, or K times the price of the option that pays 1, minus S0 times the price of the option that pays the gross rate of return. It turns out that the price of the option that pays 1 is going to be phi of negative D2 e to the negative RT. So you own K units of this option, and the cost of this option is going to be 5 negative D2 e to the negative RT. You sell S0 units of the option pays the gross rate of return. Turns out the price is 5 negative D1. And so the put price is equal to the price of this replicating portfolio, or K e to the negative RT phi negative D2 minus S0 5 negative D1. Law of one price, first principles again, all comes back together. So that wraps up this third part of lecture 14. We'll take a quick break and we'll conclude the lecture by talking about implied volatility in the next video.